everybody. Thank you very much for joining us here today. This is Paul Taubman with 9.connects. You are in the right place if you are here for our webinar on vias. So some of our objectives for today, we're going to do a sanity check in terms of the layer stack-up. Understanding the layer stack-up is very, very important because if we don't understand that stack-up, we can make a lot of mistakes in fabrication, possibly even in assembly as well, which obviously is going to be both a cost hit and a time hit as well. We'll talk about annular rings and the equations to ensure the right fit and right hit. You'll understand what I mean by that when we start talking about that. We'll certainly explore the non-traditional types of vias, the microvias, the back-drilled vias, and the vias and pad. And just as importantly, I want to talk about the documentation for these types, what needs to be done in order to get these things into your documentation set. And kind of as a little bit of a side note, the whole reason we even put this webinar together was a couple of weeks ago, somebody asked me about the back drill. And it really dawned on me, I had no clue as how to get that back drill information put into the documentation set. But today, I'm going to show you how to do it. So hang on here. It's going to be drinking from the fire hydrant. We should possibly have time for questions. It seems like every time I do this, I'm a little short in time. Other times, a little more extra time. I guess it kind of depends on how things flow. But if you do have any questions, please do put those into the GoToWebinar panel. Even if we don't have time to get to them, we will certainly get to them afterwards. And of course, if we have enough questions, we'll put together an official Q&A sheet as well. So let's get on with it over here. Okay, before we begin, I have a polling question for you. So I'd like to know if you've actually used any of these things in the past, like blind vias, buried vias, a via and pad, microvias and back drill. And yes, you can select more than one in this poll. Okay, we're going to close it over here. Hopefully you can see the results of it. So about half of you have used blind vias, and about a third of you have used the buried vias. A lot more people have used the vias and pads than I would have expected. This is really interesting, good to know. So about 3/4 of you. And when it comes to the microvias, it's still about a little more than a third of you. And very few of you have actually used the back drill via, which is good because towards the end, I'm going to show you what that whole thing's all about, at least in Altium Designer. And then from there, you can see if that's going to be an option for you. So let's take a look here. Very, very quick review of the vias. I know most of you probably know this by now, but for those people who are new to this, just want to kind of give you a quick overview of this. Because when we talk about vias, there's a lot of parts to those vias. We'll start off over here actually with the annular ring. So the annular ring is the end product because initially this starts off as a pad, and then later on I'm going to send a drill bit through this. This is for the plated type of vias. Those are the through hole, the blind, and the buried, and I'll talk a little bit more about that as we're going along. So this is basically almost a target. That's the best way to look at the annular ring. So initially it starts off as a piece of copper, and then later on that drill bit's going to go through, and hopefully it hits the center of it. We'll talk more about that too in this webinar. We have the hole itself. That hole is going to be plated, needs to be plated, otherwise we're not going to be able to get our signal from one layer down to the next. And that really, if you boil it down, that's the whole intention of the via is to put us into the Z direction, right? We can easily do things on the XY plane, but to get to the other layers, that's what the via is providing us. There's also this thing called the antipad. So if we have a layer of copper on another layer, and we don't want this via to have anything to do with that copper, then we can have the tool the tool by default, if it has nothing to do with that copper, is going to remove that copper area underneath so that there is no electrical connectivity to that copper layer. And then lastly, we have this thing called the teardrop. And by the way, Altium Designer, and I know also Allegro, has the teardrop as well. What's the idea of the teardrop? So if you've got a trace that is coming into the annular ring here, it's always nice to provide a little extra copper here onto the sides. Again, as I'm going to mention here later on, this hole is never dead center, and so it gives a little bit more of a target to hit. So using the teardrop certainly is no disadvantage, and I encourage you to use it. But it's usually kind of a post-process. You first route, and then later on, you run the teardropping function. Okay, one other thing that we also have here for nomenclature, and this gets kind of interesting, is this concept of thermal spokes. And we'll understand why they're called thermal spokes here in just a little bit. But if you see some type of pattern like this on your designs, that's because someone has put in the thermal spokes. Altium Designer by default gives you these thermal spokes. That's called the relief connect in the rules. And you can see what the different types are. They don't call them thermal spokes per se. They actually call them conductor whiffs. You can also see what they call the air gap, which is a nice way of saying the copper that's being removed. And you can control also the expansion, those type of things as well. So why do we even have the thermal spokes? Well, the other option we have is a direct connect over here. And for most vias, that may not be necessarily a problem. However, if you're using a through hole, and the difference between a via and a through hole is that a via is used for routing, whereas a through hole is primarily used for components, through hole components, that can actually cause a bit of an issue. So I found this example over here, and as I started looking to it, I saw that there was kind of a mess of problems with it, and I wanted to bring them to your attention because this is a great example of really what you don't want to do. So we have a surface mount pad over here, and that's the way they made this particular footprint, and then they put in a through hole. In this case, it's a via. You can look at it either way. They happen to use square annular rings. Okay, but when we look at this, we actually have two problems, one of which I created. And one of those problems over here is that I actually created this as a direct connect, and that's exactly what it looks like. So if this was a ground pad, in theory, this is great, right? I want this thing to have a nice solid path to ground. But from a manufacturing point of view, this is extremely problematic for two reasons. So first and foremost, over here, we're going to put, what they're going to do is they're going to put solder paste on top of this pad. And then what's going to happen is they're going to put that lead on there, and when they warm this up and they turn that, and that solder paste liquefies, guess where it's going? It's going to drain right down this through hole over here. So you're not going to have a good joint if there's any joint at all. You're just not going to have a good connectivity to it. The other issue that we're going to have, and that's assuming we had the thermal spokes, if we do a direct connect over here, depending again how we solder this onto the board, we might actually get a cold solder joint or the lack of a joint altogether, because what happens is that copper is a phenomenal has a phenomenal capability of pulling out heat. And when we do a direct connect like this, we may not actually get enough heat to liquefy that solder paste. And so we get what's called a cold solder joint, or it may not even bond to it whatsoever. Either way, that's going to be a reliability issue. So when it comes to direct connects, you can certainly use them on vias, but make sure that you don't have a via that's in close proximity to a pad that's going to get soldered on, whether it's a surface mount pad or a through hole pad. But I know this kind of went off on a little bit of a tangent, but when I started seeing this over here, I said, whoa, I better bring this to people's attention. 10 years ago, I've been totally blind to this. Now, as I've done more research on these type of things, this is becoming very evident to me. So hopefully you'll see those type of things too. We don't want to do things like this because of reliability and assembly issues. All right, let's move on over here. So I want to go through all of the via types over here. Some of them, you know, probably by the back of your hand. One thing I've always found interesting, though, and this is a nice feature of Altium Designer's 3D, is that we can actually look at this thing as it probably would look. It's an ideal situation, but this is generally how it actually would look in the design itself. More often than not, what we have here on the right side is what's called a coupon. So we'll either see an actual picture of this where they've actually sliced through this thing called a coupon, or they're going to show you a graphical version of it. They always show it being sliced through, which is great, but then you don't really get a full flavor as to what this via actually looks like. And of course, we don't really use translucent materials, so to see something like this is kind of rare. Let's talk about this coupon here for just a moment, because you may say, well, what's a coupon? When I was first asked, did I want a coupon with my board when I was working in the defense industry, I said, well, certainly, how much am I getting off on it? And I started laughing. But what a coupon really is they will put structures into the panel. So when you make your board, they put this into a panel. And so they can put structures on the outside of your board, so it has nothing to do with your board itself. And then what they'll do afterwards is they'll actually cut through that part, and then they'll look at things here. So they want to make sure that the plating is good. They're also going to want to make sure that the registrations are good as well. So when you get into these things like 18, 20 layers, even at 10 layers, they want to make sure that the registration between these layers looks really good. So they'll make these coupons and then cut them out, and they're just to basically look to make sure that the quality of the fabrication process was indeed there. It's a kind of a verification for them. So, but anyways, what I want to do is show you as many of these 3D graphics as possible to give you a full flavor of it. Here's the through hole. Good old-fashioned through hole. It's been around for about 60 years. It goes through the entire board. Our major advantages, it is by far the easiest to fabricate. So when you get a cost for a board, the through hole generally has already been accounted for in that cost there. The only time that cost may go up is if you hit over a certain number of through holes in your total count. But nevertheless, it's not going to be substantially more to do that. And of course, it gives you access to all the layers, which is just great. So this is an 8-layer board example, and I pretty much would have access to and from any layer I'd need to through this. Of course, the disadvantage is they take up board real estate, And in high speed, we get something called a stub. Stubs are bad business in high-speed design. So what do we mean by that? We're going from layer 1, dropping down to layer 5 in a particular example, but we're not doing anything from layer 5 downward. That's a stub. And in high-speed design, that stub is going to basically cause a reflection, and that's going to cause signal integrity issues on that particular line. All right, let's take a look at the next one here. The next one we'll take a look at is the blind via. Excuse me. The blind via here just basically either starts on the top or the bottom, and it ends on an internal layer. So obviously the advantages over here is that you'll have no or less stubs. Now I put the caveat less stubs here because just because you use a blind via does not mean that you're totally getting away from a stub. For example, if I have a blind via that goes from layer 1 to layer 4, and I happen to use one of those blind vias from layer 1 to layer 2, well, guess what? From layer 2 to layer 4, I still got a stub. So be careful of when you're using these things because, yes, they can they'll definitely reduce the stub, but also just keep in mind where you're starting and stopping from on a given layer here. They are great with assisting with BGA breakouts. So if you're familiar with ball grid arrays, that's exactly what's underneath these parts. They have these little solder balls underneath. So here on this picture here, if I get my cursor up, and the picture over here, we have the land. They call the surface mount land here. We have a little bit of a trace. This trace over here is covered with solder mask so that it doesn't, so that solder doesn't ooze out into the hole over here. So it's acting as a barrier. And then we have a blind via. We can also certainly use the through hole via as well. So that's the idea here, is that we have all of these pins that need to get out and routed, and so we want to send them down to the other layers. So this is called dog boning, and blind vias, and of course through hole vias can certainly be used to do that. In this particular case here, we would gain real estate because we don't have to go down any further than necessary. Of course, the disadvantage to that, we're going to talk more about the fabrication process. Anytime we start adding more things to the fabrication process, it's going to be more money. And more importantly, we've got to understand the fabrication process itself. Because if we, in Altium Design, or in pretty much, by the way, any tool out there, if you start putting blind and buried vias as you see fit in terms of the start layer and the stop layer, you may create something that just can't be fabricated. And that's why it's really important to understand this fabrication process. The other one over here is the buried one. So we don't see this thing. It's completely encapsulated in the solder mask and in the buried layers of the PCB design. Okay. What are their advantages? Certainly, again, no or less stubs. So again, be careful. Just because it's smaller does not necessarily mean that we could still create an opportunity for a stub. And the big thing, of course, is that you're gaining real estate, usually both on the top and on the bottom. So that's the big thing there. So if you're doing a lot of routing, these things are very, very useful. What are disadvantages? Well, the same thing that we saw with the blind ones. It's going to cost more money, and you got to understand the fabrication process. But here's another thing too, and I come from a test background. There's nothing more maddening than when you have a problem on a board and you have no way to access that signal. So if, for example, you're doing two BGAs and you're using internal, basically buried vias in order to route between the two, and there's an issue, you're going to have to start doing destructive work onto that board in order to get down to that copper. And it's not pretty, and it's very frustrating. And of course, there's a lot of agony because you don't want to do something. A lot of times requires a drill or a Dremel to get down there. And of course, with things being so small, it's really easy to do some damage when you're tearing things up. So just be aware that if you're going to use these things, that you have a test plan so that you can get to them. All right, these things called microvias. Looks like a lot of you have started to use these, which is cool. And I'm going to be honest with you, though, they are still a lot more expensive. I'll jump to the disadvantage in a moment. I really tend to believe that with the size of the boards and the size of the components, this is probably going to be just as common as the through hole, probably in about another decade or so at the rate things are going. So what is a microvia? And there's two types. There's stacked and there's staggered. You can see the stack that's over here. I'll talk about the staggered one in just a moment. But it's usually one layer. You can get down to two layers when you do these, but most people keep these down to one layer. They are definitely 6 mils or less, and in fact, it's not even in mils, because in this type of process, you're actually starting to get into the micron range, which is really phenomenal at that point. So they can get really, really small. There's the use of a laser to drill here. So we're not doing the classic, what they call drill and plating. So the through hole, the blind, and the buried, which I've just shown you here a couple of minutes ago, those are your classic ones where you take a classic drill bit, you send it through, and then you plate it. these will also be plated as well, and we'll talk a little bit about that later on. We're no longer using a traditional drill bit. We've got to use a laser to do this, and they can do it with amazing precision. Because remember, in a sense, you know, the computer chips that are out there, right, we're starting to get down to the micron level on our printed circuit boards, but that's exactly where computer chips were back in the 1970s, right? I mean, there's companies called Micron, or there's a company called Micron out there because that was the size in which they were doing their computer chips. Now they've gotten to nanometer technology, but a lot of those practices can actually be applied now to the printed circuit board, which makes this really exciting. So anyways, that's what we've got here is the use of the drill. The advantage here, of course, is that you can connect layers as needed, and that's what they did here. So this came from a company called TTM Technologies, and what they did is they took a 10-layer board and showed that they could actually stack these things. Now keep in mind, this is not done all at once. These are done layer by layer by layer, so that's where a lot of the expense is, because again, every time we've got to stop our lamination process to get these layers together, we have to add a lot of extra processes in here in order for this to work. And as a result, this would be something that you could certainly do, but it would be rather expensive. So it is more expensive, as I just mentioned here. The other thing that happens over here is that it's less able to handle flexing a board. So if you've got a board that's going to go into some environment where there's going to be a lot of flexing of that board because of, let's say, G-forces, or this thing is just bouncing around quite a bit, what's going to happen is you may get a stress fracture where this is. So normally what happens here, where my cursor is on this example, is that they're going to drill out with the laser this dielectric here. And then what they're going to do is they're going to drill it out until they get to the copper. And then from there, they're going to plate and or fill that copper here, and then they're going to plate and then smooth out the top here. So as you probably have seen with anything else, that if you have something that's already there, that's rigid, and then you pour something on top of it, yes, it will bond, but no, it's not a great bond. And so yes, these will bond together, but you start putting any type of stress onto it, and it will fracture on there. So they've gotten better about that. But right now, that's probably the biggest concern about using these things in any type of harsh environment. So just keep that in mind. As for Altium Designer itself, Altium does not have a special way of showing this. So what I did here was basically I routed this out. This was a one layer, so I set this up in the drill pairs here, and then I just stopped. And then at that point, I continued. I put down another one of these vias here, and then I continued along. So that's why you see what I'll call the poker chip here. We start on the top, we go to layer 2, which is green here, but notice that this is a light blue, because what I did here is I put in another, what would be represent as a microvia that would go from green to blue on out over there. So you just treat it like a normal via, and your fabricator is going to know very quickly if this is going to be microvia, because A, hopefully you talk to them about it, and B, just the sheer size of it, they're going to know it's going to be a microvia. The microvias also being staggered here, this puts a little less stress on things, whereas this over here, you've got a lot of stress points on top of each other. This removes a lot of that particular stress. So all of this information over here is the exact same as what you saw before, but just what they call the staggered versus the stacked there. And again, it puts a lot less stress on stuff that's being built on top of each other. Excuse me. The last one we'll take a look at over here is this thing called a back drill. So this is the through hole with the stub removed. I suppose you could also do this with a blind one, a blind via as well, but it's primarily for a through hole situation here. The advantage is definitely much cheaper than microvias, at least at the time of this recording. It may be on par with the blind and buried via costs. That's something you want to talk to your fabricator about. And it will also allow for the use of any layer again, which is kind of nice, right? So we're getting that ability to use whatever layers that are necessary or available to us without necessarily worrying about the stub. Okay. Of course, the disadvantage is there's extra cost, right? Again, we're adding additional cost to our fabrication, and we don't get the real estate back over here, right? We can't be basically routing underneath this because we're going to send a drill over here to bore out that stub. So that's basically how that works. The other one is the via and pad. So there's no picture representation of this in Altium Designer. It's really something you call out as a post-process. So what do I mean by that? So if you take a look at this through hole, this picture over here, it does a really great job of showing this. The via and pad is really done after everything else is said and done. So if you had a through hole over here, what they're going to do here is they're going to go through the process of capping down the bottom. They're going to fill this with a material. It could be both conductive or non-conductive, because remember, your hole has already been plated at this point in time. And so the idea over here is to put a material in here that's not going to outgas, and it's going to be able to support this copper plating that's done on the top here when heat is being applied to it. And nor do you want it to actually, round out or bubble in there. So that's what they're doing here, is they're filling out the material here to support this, and they're going to plate that over. When would you use this? Well, when we looked at the dog boning over here, we had a lot of opportunity to get that dog bone in here in something that's what's called a fine pitch or high density pitched part situation like this here. There's no way we could dog bone this. So this is when you'd use the VM pad. The advantages of that is that when the dog boning is going to work. There's also another thing that someone brought up as well, and I think there's a truth to this. You're going to get what's called an RC in this path here. And why is that? Because if you think about it, when the signal is coming off of this here, it's going through a trace that's also got some solder mask on top of it. Well, that's going to change the impedance. And then from there, you're going to go back into this via hole over here, and the solder mask again has been removed. So now you've got yet again, you've got impedance change. So you're adding RC to that particular path, whereas over here, you're removing that by just simply having that signal go straight down from that solder pad. So that's another thing to keep in mind as well. The disadvantages, of course, like everything else, it's cost. Now, let's talk about how big or how small a via has to be. We need to start with the hole, and that is known as the aspect ratio. So that is the width of the hole, and that ratio is 10 to 1. Well, 10 to 1 of what? Really, for every mil of depth, the hole should be, actually this should be for every 10 mils of depth, the hole should be 1 mil wide. So that's kind of what that should have been over there. But that's the point I'm trying to make, is a 10 to 1. So every 10 mils of depth, the hole should be 1 mil wide here. If you're doing high production stuff, like stuff that you're really trying to push through, so it's not necessarily about quality, it's just really just stuff that is pretty simplistic and you're just trying to get it through as fast as possible, they may ask for a width of hole of 6 to 1 for that. Most companies can do 10 to 1. Some of them compress it to 11 to 1. That's something you want to talk to your fabricator about. But the whole reason you want to know about the hole is because obviously you want to make sure you can give something to the fabricator that they can do. Now again, this aspect ratio is for drill in plate. So through hole, blind, and buried vias. This would not be applicable to microvias. Okay. Let's take an example over here so we can take a look at this, because there's some caveats to this as well. There's an 8-layer board. This 8-layer board that I have here, you can see this example I've got, is basically 69.7 mils. We're going to round that to 70 mils. And that is going to give us a 7 mil width, and that's perfectly fine. So what I wanted to bring to your attention here is that when it comes to plating and drilling, the drills below 10 mils are actually an even number. And this is something I've heard from not only a fabricator directly, but this is also even in the CID manual as well. So just keep in mind that below 10 mils, they're going to use an even drill, like an 8-bit or 6-bit type of drill at that point. So yes, I have 7 mils over here. The question is, can I make use of the 7 mil? And the answer would be yes. So I don't have to bring it down to 6. And the reason I don't need to bring it down to 6 is that my 7 mil hole over here, when I put this into Altium Designer, is considered to be a finished hole. What the fabricator is going to actually do is they're going to drill an 8 mil drill, and then they're going to plate it afterwards with one, and it's going to be 1 mil of copper over there. So just kind of keep this in mind here. So if you do get, let's say for instance, let's say this number came out to 8 mils width here, then more than likely the fabricator would use a 10 mil drill, and you might actually get a 9 mil hole there, just because again they're going to use an even drill. So just be aware of that. Now the process itself is really, really messy. So I came up with a couple of illustrations here to show how messy this process can be. Let's take a look at this here. So here's the first issue we have with our drill. I alluded to this earlier. One of the problems that you have is that you never hit dead center, especially so. That's really why are we talking about this, and let me take a step back. The reason we're talking about this here is because we need to now figure out what the annular ring size is going to be. So we already know what the hole is. How big of an annular ring do we need? And the problem that we have is that there are manufacturing tolerances at play here. So we don't want to make something so small that everything's going to fail yield. So what are the problems that we're going to have? Well, first and foremost, we could have this off-center drill. Okay, so if we don't have enough space or a pad or a target over here, we may do what's called a breakout, and if it has a breakout, then for certain classes of electronics, they'll actually fail it, even though it might be electrically sound. They have to fail it, especially for Class C. Okay. Another thing is that we may go in at an angle, at a drill angle. So if we have a really thick board, for example, let's say it's a 1/4 inch board, 20 layers, something of that nature over here, we may have hit dead center over here, but if this drill is going in at an angle, it may not be hitting this thing at all by the time it makes it out the other end, or we have, again, what's called breakthrough. We have a layer misalignment. So even if we did hit this thing dead center on, if we've got a lot of layers and there's a little bit of an alignment, and this can happen with really large boards, especially as you go away from the center, we could have this misalignment, and that could be a problem. There's also drill bending. When you start getting below 10 mils, those drills are going to start bending. Remember, if you're going through a dielectric, that dielectric actually has a glass weave in it, so it's going to try to find the weakest point in that weave so that it can make its way through. So you are going to get some drill bending, what they call wandering, and of course you can get all of the above. So these are the things that we have to deal with. We want to make sure that this annular ring is going to be big enough so that we're not going to have problems when it comes to drilling and plating. So what is the rule for this? Well, the rule is something that comes from the IPC. It's A plus 2B plus C. So A is the diameter of the finished hole, which is what we've already figured out. The second one is B, the minimum annular ring. So this has always drove me a little crazy. What do they mean by that? But really what they're saying is the minimum space that you'd want between the edge of your annular ring and the edge of the hole. Okay, so that's the minimum annular ring. And as a matter of fact, here's for Class 3 over here. In Class 3, they need at least 50 micrometers. Class 3 are your high reliability products, like your stuff that go into aircrafts or into medical devices. This over here is what they call a breakout. Class 2, it's acceptable, but for Class 3 mature products, this is not going to be acceptable. And then there are fabricator tolerances as well, and all those fabricator tolerances take into account all this nonsense that can go on during the fabrication process. So here's our example. So I'm going to take an example of an 8 mil hole here. I want about 2 mils pad clearance edge, and I want to use what's called a level C. So this one is there, meaning that I'm only going to allow for 8 mils of fabrication tolerances to take into account. So if I did like a Class A, I think that's about 16 mils. But this level C here is, I'm going to use the 8 mil one here. And I got to be perfectly honest with you, I think that fabricators can easily do better than 8 mils for the most part anyway. But just to keep this conservative, what I'm going to do is I'm going to add this all together so I have a 20 mil diameter annular ring. Now, in looking at some of the examples we've done, a lot of times if we had an 8 mil hole, we probably have a 16 mil annular ring. The point I'm trying to make here is that if you haven't talked to your fabricator, go with the conservative number. Talk with your fabricator, because they could say, oh, well, I can do this in 0.5 mil pad to pad edge clearance here, no problem, and I only need 5 mil of tolerances. So, they can drop this number down dramatically, which in turn is going to give you more real estate to work with. That's the big thing I really want you to walk away with this here, is talk to the fabricator, because it really is a chain reaction. You talk to them about the number of layers, and in turn, that's going to give you the board thickness. The board thickness is going to give you the minimum hole size, and for the minimum hole size, you're going to get the minimum annular ring width, right? And then, of course, the class of board over here is going to affect your yield and your cost. So see how these things kind of propagate one after another after another. The old days of going to the fabricator after you're done with the board are really over. If you're not talking to them from the get-go, you're going to have a lot of problems afterwards. So, all right, we talked about the fabrication of the vias. Let's take a step back and talk about the fabrication of the board, because this also has a lot to do with the types of vias that we can choose. Let's talk about the three main materials. The first material is this thing called core material. And a core material is nothing more than a hardened dielectric. And when I say hardened, it still can be flexible, but it's a hardened dielectric with copper on both sides. So it's not going to get mushy under heat. It's already been pre-hardened, okay? And so there's copper on both sides of it, and then they will etch off the copper on each of the sides based on the image you give them. So, for example, this little sample from Rogers Corporation, that's exactly what they did here. And as I mentioned, some of the stuff is pliable, some of it's not. Okay, it all depends on the material that you're using. Again, side note, and I think we've mentioned this many times before, it's worth reiterating, if you don't know the materials you're using, talk to your fabricator, because you may find a material that is just phenomenally great at what you think it might or can do for you, but it can cause a huge mess or a problem for the fabricator. Always talk to them about the materials you're interested in using. The next thing is the pre-preg. This is just simply a glue layer. Let's just call it that. It has nothing really to do with the copper. It really has to do with gluing layers together. So once it gets hot, it gets sticky, and it allows us to glue things together here. And then lastly, there's this thing called copper foil, and sometimes we need to use a copper foil. And in one of the configurations that I'm going to show you, they would make use of a copper foil in order for us to create a layer so that we can etch it out. So let's talk about the fabrication process. And before we do that, I want you to think of a house and how they build a house. So think of them digging out the ground and putting down a foundation. And then from there, they start building the first floor. And when the first floor has got enough structure to it, they may start framing up the second floor. Right? And that's how they build it. They build it from the bottom up because we have to fight this thing called gravity. That's not how they build anything in fabrication, in PCB fabrication. There's two ways they do it, and I'm going to show you each one. The first one is what I'll call parts to whole. So you take smaller layer sets and you combine them together. So let's look at this 4-layer board here. What we see here is 2 core materials, and as I mentioned earlier on, this stuff has copper on the top, copper on the bottom. So they'll take one of the cores and they'll etch out layer 1 and layer 2. They'll take this other core here and they'll etch out layer 3 and layer 4. They'll take one of our quote-unquote glue sheets, our pre-preg here, put it between the two, and then they'll do the lamination process of the heat and pressure, and boom, you've got your board together. And then finally, they'll drill and plate the through-hole via, at least if that's what you're using here. And then lastly, they'll do the solder mask. So that's the concept of part to whole. The other way is inside out. So what they'll do here is they'll take a core and they will etch layers 1 and layers 3 on that core. And then afterwards, they'll take a sheet of pre-preg and a sheet of copper foil, and they'll do the same thing on the bottom, and they'll laminate it all together. Then they'll etch layers 1 and layers 4, and then after that, they'll drill and plate the through-hole via and then add the solder mask. So why is this important? Because it depends on whether or not you want to use a blind and buried via. So in our first example, we went inside out here. I can do a buried via because I know they're going to start with layers 2 and 3 because they're going to use a core material. So after they're done with 2 and 3, they can drill it and they can plate it, and then they can continue on with the process. Another way we could do is if I wanted to have a blind vias on the top and the bottom on this 4-layer board. Guess what? I can do that as well. But instead, I would start off with a core on the top and a core on the bottom. And as I just described it, we would do 1 and 2 for the first core, 3 and 4 for the other core. We'd stop that process, drill and plate it, and then we would continue it on our way there and continue with that process. So that's why it's really important to understand how they're going to stack this thing up. And that's why you want to have that conversation with your fabricator, because in one situation here, this works really good for a buried via, and the other situation works really good for a blind via. Now, I want to do a polling question, but before we put the polling question up, I want to kind of give you the setup scenario here. So take a look at this over here. What I'm doing is I'm going to do 2 blind vias. So I want to do 1 from 3, and I want to do the other one from 4 to 2. And my question to you is that, putting aside the use of microvias and back drilling, are the blind vias manufacturable? So go ahead and let's put that poll up there. Okay, we're going to close this up over here, and so we can see, okay, so this is kind of interesting. So 66% of you said no, and 34% yes. So generally speaking, the answer is going to be no. Now, fabricators can work amazing things. So some of you may say, well, yes, they could do it if they did this or they did that. But from a normal process here, this would be very, very difficult for them to do, because after they've cored this over here, for them to drill down over here and then plate it would be very, very difficult to do. Because remember, 1 and 2 would have been fabricated on the top and the bottom. 3 and 4 would have been fabricated on the top and the bottom. They would have had to have laminated the pre-preg here, and then they would, if they were to try to do this, what they would have to do is drill this all the way down, make sure that they didn't tear up 3, and that's where it gets really ugly. And then they would have to, with the drill, and then they would have to plate that. Really hard to do with a drill and plate method. Microvias, it would work, but that's why I said, putting aside the idea of a microvia or even a back drill, for this to work, it would be it'd be difficult, if not impossible. So the takeaway I want you to take from this here is that if you see something like this where you see an overlap, question it. Make sure that the person doing this either is planning on using like a microvia, or they're planning on using a back drill, or just make sure that they understand this whole fabrication process we talked about, because if they don't understand how this thing's going to be put together, they're going to be sent back to the drawing board, and they're going to have to do a lot of tear up of their routes to get this to work, and that could easily be 2 weeks of effort. I keep talking about this thing called cost. And I wanted to just bring this to your attention because every time we add in another type of via other than the through hole, we expect a through hole, right? Otherwise, we won't have multi-layer boards. But if we add in other types of vias here, every time they have to stop that process and they got to drill and plate, this is exactly what they're going to go through. So all 10 of these steps is for the through hole. 1 through 8 is what they would do for all the other types of vias. Even the microvia would have at least 6 steps to this particular process. And the reason why is it's not just a matter of just simply drilling this thing and then plating it. There are things that they've got to do in order to get this all set up. And a lot of it is really setting up masks, which they've got to etch on, and then later on they do the copper, and then they've got to etch off those masks over there. So the process is very similar to the way that they actually etch off material on all the layers. It takes a lot of steps to do that. So the point I'm trying to make here is that the more different types of vias that you have, okay, the more, like, let's say the blind or varied vias that you add to this, you're going to stop that process over and over again so that they can do this whole plate and drill. So just keep that in mind. All right, let's talk about microvias here for a moment. So by definition, they tend to be 6 mil or less holes. Anything bigger than that, you probably can do plate and, drill and plate. You need at least 2 mils for annular clearance ring here. Okay, and I think that's probably getting even too big for the ones they can do these days. What's the process? Really, they're taking a laser to etch out that dielectric there rather than a drill here, and you can do either copper plate only or a fill-in plate. Now, I bring these 2 pictures to your attention here, and I wish I could spend a lot more time on it because I think that microvias are just a topic all itself that needs a lot more review and investigation. But if you want something in the meantime about the cost elements of microvias, there was a really great YouTube video called Worth Electronics. Take a look at this. In fact, I took these 2 images from this, and what they were trying to show is the cost of doing certain things. So here it is with just it being plated. So the idea is that they drilled through and they just simply plated this over, versus over here where they drilled it and then they filled it later on. So you can either do a fill with a conductive material, so this is all copper, or you can do it with a non-conductive material. What they were showing over here is it's a lot more money to do this versus this. However, it depends on your reliability again, because what will happen over here is this is the end product, and what they did is they sliced through it, and what you're seeing here is an air bubble, which makes all the sense in the world, because what happened was is that when this solder bump was probably put on top of this at the very beginning, there was air all around it. There was air in the gap, there was air near it, and so when it started to melt, all of a sudden that air started to rise, right? So now you got a bubble over here, but then it hardened fast enough to trap it, and that can be a reliability issue. So for things that don't have necessarily a major reliability issue associated to them, you could probably get away with this, but if you have a reliability issue that you're trying to avoid, then you'd probably want to spend the extra money on this. And they made that very clear, is that we can't tell you which one of these to use. We have to understand your situation. What about so let's talk a little bit more about what we need to do in Altium Designer for microvias. So in Altium Designer, it's really treated the same way as any other type of via here. You declare them as single pairs here. So by default, Altium will always give you your through hole here. There's one I left in here. This is basically a buried via. But if you look here, if I want to do this in a microvia fashion, I would do it from L1 to L2, L2 to L3. This one should have been L3 to L4. I apologize about that. But that would be the idea behind that as well. So just make sure you set up your layer pairs as such. And then you've got your constraints. Altium always defaults to 10 mils. So obviously you're going to have to drop this down to 1 mil or possibly less, depending on what the fabricator is going to allow you to get away with. By the way, the accuracy of Altium Designer, at least in the old coding, I don't know if they changed this with the new coding they did, but in the PCB editor, when I worked at Altium, you could get 6 places if you're using imperial, 3 places past the decimal if you're changing it over to metric. So just to be aware of that. So you can get some pretty good accuracy in there, even though I don't believe they have a micron at this point. I know Allegro has a micron grid, but Altium isn't there just yet. Okay, no special DRCs except for the routing hole size, which you just talked about over here. And of course, you've got to adhere to the requirements set forth by the fabricator on this here. So don't just put things down blindly thinking that the fabricator will figure it out. They really have got to give you their limitations on what they can and can't do. And documentation, what I mean by as usual is that it works the same way as any other plated hole, right? Whether it's a through hole or a blind or buried via, Altium is going to take care of that documentation for you. Via in pad and Altium Designer. The only way you're going to get this here called out is through the fabrication notes. And that's what you're going to have to tell them. You're going to tell them which component or components require the via and pad. Okay? And why is that? Well, if we think about it, there's a gap in the documentation. Things like ODB++, Gerber's 2581 from the IPC, they talk primarily about the layer information. What's the copper that you have on each one of the layers? And yeah, I know they get into bill of materials and other things like that, but really it boils down to them discussing what's on the layers. And we have the NC drill file that tells us what we need to drill out, okay, and whether it's going to be plated or not. And then lastly, what really calls out a fill and a via. So we really don't have a mechanism to call that out. So that's why it has to be a fabrication note at this point in time. Now, let's get on to the back drill. This is where it gets kind of interesting. So the idea here is that we're going to start with the through hole, and then we're going to bore out a stub. And in Altium Designer 18, they do a pretty good job of showing that. So that's the picture from 18 here. So we're going to take an example of an 8-layer board. Our intention is to route it from layer 1 to layer 5, and we want to bore out layers 6 through 8. Okay. Now, let me talk about this before we put the poll over here. I spent quite a bit of time trying to figure this thing out, and I want to give this polling question here because if you go with a certain philosophy, it won't work. And I want you guys to kind of think of this for a moment. So to use the back drilling in Altium Designer, we must declare either the start and the stop of the copper, the start and stop of the bore, both of them, or neither of them. So go take a guess as to which one is correct. Okay, so we're going to close the poll over here. So a little bit more than 50% of you said both. About 20% said the start and the stop of the bore, and 21% said the start stop of the copper. And then some of you are going to say, okay, this is a trick question, so you went with the 7%. So here's the correct answer: the start and stop of the bore. Okay. Now, when I first went in there, I thought that the back drill was a property of the through hole. And that's why I was having such a difficult time trying to figure out how to make this thing work. And if you look at the 2 preview videos that Altium did on there, it kind of gave that impression. But that's not how it works. You actually are telling the start and the stop of the bore. So if you go into the drill pair manager, all I need to do is show that I've got a through hole, which again is default for anything that any board. But then what I needed to do here is show that from L5 to L8, I want it to be back drilled. Okay. And it's really simple to do. It's a matter of getting the add button here, saying the first layer can be 5. And by the way, you can say 8 to 5. It doesn't matter. Altium recognizes that these are going to be back drilled. There's a little checkbox that just says, hey, this is back drill, and that's why you see the BD over here. That's all I needed in order to declare that this through hole is going to be back drilled from layer 5 to layer 8. All right. The second thing I have to have is a high-speed design rule. Why is that? Because back drilling is not a property of through holes, and that was what was driving me crazy when I was trying to get this to work together. It really is a primitive all its own, but it is driven only through the layer pair, the declaration of layer pair, and it is driven through a rule. So there's no way you can really click on a back drill and look at its properties. So it has to be driven all through a rule over here. It's kind of like a room if you think about it, right? If you dealt with rooms in Altium Designer, yeah, you can click on it, but most of it's driven by the rules. Here, it is strictly, the back drill is strictly driven by the rules. It is the max stub length back drill. So we've got to provide a net or a class. And more importantly, we've got to tell it that it's a via, because if we don't tell it it's a via, you could actually also drill out a through hole, and that's not what you want to do, because I want as much copper as possible on a through hole. So make sure you put that in there. So here's the net class example. So what is it trying to do over here? Well, it's going to tell me what the oversized drill is in order to bore out that copper. So keep in mind with the back drill, that plate is already done. So I'm going to take that copper out now. That's the whole idea behind it. And then how much is the max stub length I'm willing to allow? So you're never going to be perfect, right? So even though I want everything below layer 5 to be removed, right? And of course, in theory, I'd love to be right up to layer 5, so there's absolutely no stub. But let's be realistic over here. We've got a drill that's going through this over here. There are tolerances that we've got to deal with. So as a result of that, leaving a little bit of a stub length is going to be okay. I think 15 mils is a little much, but nevertheless, that's, I think, the default of it here in this example. I take that back. I think it may be 5 mils. I may change that to 5. So I was probably doing this to exaggerate some of the pictures. So I'm not going to blame this one on Altium. That's just probably my doing and taking a picture of it thereafter. The next part was we're going to simply route it the same way we route everything else, right? We just hit we start our place. We use our, we can use our keys on the numeric keypad to drop a via, and then we can continue on to the layer of desire. When you're done with this, you want to check it to make sure that it worked. And this is another thing that really kind of tripped me up. When you look at the top layer, here's layer 1. I didn't know that the back drill existed. It's not until I went down to layer 5 where I continued my route that I can see this outside poker chip. So that's what they show over here, and hopefully you can see this. In fact, I'm going to go, I purposely did this so you can see this a little bit better. It's not easy to see on here, and I wish Altium would make this a little bit thicker, but nevertheless, it's there. So what you're seeing here is the same color, which always represents a through hole. So you don't see a split chip in terms of one color on one side and another chip on another side. That's reserved for blind and buried vias. So it is showing the through hole. But what they did over here is you can see that this color band here, which starts on layer 5, and then they have the dark blue color band, which is layer 8, which is the traditional bottom layer color there. And so now I know this has been back drilled. Okay. In terms of the documentation, let's say human readable documentation, if you're successful in getting that to work, all right, so if you see this over here, like, yes, I got it to work here, it's going to show up in your drill tables. And you can see that right here on the second line. So I put only 1 here so that we can easily read this out. Ignore the 20. That just happened to be a through hole connector that I used in order to do some routing here. So you can see that we've got our plated through, which is L1 to L8, and then you can also see our non-plated one. So that's the one that's going to get bored out. Notice it specifically is back drill from 5 to 8. Also notice it's 29 mils. Why does it say 29 mils? Because we asked for 0.5 to be on each side, so that's why it's now 29 mils as opposed to 28 mils. What about the documentation of this? It's all contained in the NC drill files. So when we do our file fabrication outputs NC drill files, or we use our out jobs here, this is what you're going to get. I recommend you split them up. You don't have to, but this will just, for your knowledge, that you have both the plated and non-plated holes. These are all the files that you're going to get as a result of running this setup over here. Let's take a look at these really quick, because a lot of times people are like, what am I supposed to do with these things? The DDR just gives a summary of the types of tools, the hole sizes, the hole counts that are going to be necessary. Here you go. You can see it specifically calls out the back drill from L5 to L8. I also put this over here. This was an interesting one. I had to kind of figure it out. So what it's doing is it's telling me what layers were used in the Gerber. So when I generated the Gerber files, I noticed it stopped at 5 and it didn't do 6, 7, and 8. Well, why is that? Because Altium didn't put out any pads on 6, 7, and 8. And that's what you're kind of seeing over here when I took the Camtastic shot. So we started on layer 1 here. You can see this went from layer 5. And I think I did another layer over here just to kind of show this. But here's the bottom layer. And the point I wanted to make over here is that you don't see the bottom layer here really for this through hole. It's a little tiny hole, but that's all it recognizes. I mean, I don't even know why they put copper on that, to be perfectly honest with you, because it's going to get completely bored out anyway. This is one of the main files you need to give them. So it's going to be the project name, and then it says dash back drill. So if you did do a back drill, it literally would have a file name with the word back drill in it, and this over here would represent that drill, that back drill requirement for the pneumatics. And I only did one of them, so it's pretty easy to see this file, as opposed to where you've got a bunch of them here. So now you can see all the hits when it comes to the plated stuff. There's also a status report here as well. Okay, so can you send all these? Yeah, they want these, especially these last two here. They want the plated and the back drill. But if you want to send them the reports, they'll make use of it as well. They'll put that all together in their CAM files and get it ready for their fabrication if you give it to the fabricators. Worst comes to worst, they won't make any use of it. That's perfectly fine. So there's our presentation here for the vias. I know there's so many other great things that we can cover. I have one more polling question for you. I'm kind of curious to know if you guys would be interested in a webinar on microvias. So we're going to open that poll here. So, all right, that's pretty cool. So 81% of you said yes, so there's definitely an interest there. So we'll give that a great consideration here for the future. So with a little bit of time left that I have, I'd like to answer possibly a couple of questions if I can. In the meantime, go ahead and look at your questions panel over there on the GoToWebinar panel. Feel free to write those in. And while you're doing that, let me just talk a moment, too, about 9.connects. You're here for a reason. And let's face it, in this case, when it comes to vias, is to review what you know and to add to this knowledge, because vias are really a subject all its own. And a lot of us, and I'd say some, I think a lot of us have learned through the school of hard knocks when it comes to vias, right, one way or another. And also, it really does take time to research this stuff. As I said, with the back drill stuff, it wasn't trivial to kind of figure out what we needed to do in order to make the back drill worked. It was there, but we just got to spend the time to do it. And you know that, hey, when you're trying to get a project done, the last thing you want to do is start fighting with a tool. So we get that. One of the things we provide here at 9.connects is coaching. And so coaching is a little bit different from our training. Training is our rigid, we follow a manual. We have an instructor that follows his manuals. It's usually a set amount of time, like 3 days. And we do these trainings throughout the year on different topics like our PCB foundations or Altium boot camp or our spec op classes. But when it comes to coaching, the whole reason we put it out there is we know that there are things that are, let's say, missing or soft in your knowledge, and you want to enhance that, and you know it's going to take you a bit of time to do it. That's when you can come to us. Coaching is basically buying or purchasing a set of hours. We do them online, and we normally work these from 2 to 4 hours. We can't treat this like support because we just don't have enough people to do that type of thing. But the idea is that if there's something you really want to learn, and it's going to take a little bit of time, and instead of you trying to go through all of this stuff to try to find what works and what doesn't work, more often than not, we have that knowledge here at 9.connects. It's a matter of us just simply meeting and making that happen. And it can be on tool processes. Like, for example, one of our customers asked me to show them a multi-board on their project, and it worked out really well. So that was the idea of doing that. Or design processes like library methodology, or things like VIAs, or high-speed design, or DDR3. Again, we can help this out. So coaching is there when formal training is not going to cover the exact same thing, the exact things that you want. So more information about that, check us out here at 9.connects.com, and you can find out more about our training. So again, thank you very much for your time, and you have a wonderful day.